that kind introduction. As Fernando mentioned already, my name is Kjell Bettgenhäuser. I'm working at Ecofys in Germany and would like to present you the key results and the methodology of a study we recently finalized for the European Heat Pump Association. The title of the study is Heat Pump Implementation Scenarios until 2030. To start with is the key research question. European Heat Pump Association came up with a question, how can heat pumps contribute to the long-term EU energy and climate targets? And that's the key question we are working on in that study and trying to analyze all the different factors and drivers and see what's the potential within the European building stock for heat pumps. So that's really the underlying driver to all of that study. A short agenda. The following presentation will be done in two parts. In the first 10 minutes, roughly, I want to give an overview on the objective and the key messages. So what's the outcome and what is the scope of the study? What did we do? That everybody knows what it is about, to get a feeling for it. And then the second part, I want to go into the details a little bit, say something about the methodology we used, more details for the scenario definition, and give detailed results both on individual building level and for the scenario calculations we carried out. And in the end, a conclusion to the study. For the first part, the overview. What's the objective of the study? As mentioned before, we did the study for the European Heat Pump Association, and they asked us to have a more detailed look in 8 European countries, which was Austria, Belgium, France, Germany, Italy, Spain, Sweden, and the UK, and to analyze the potentials of heat pumps in these specific countries. The reasons that we took out these countries is that they are the most important heat pump markets in terms of sales. So they are the most important markets in Europe for the European Heat Pump Association members, and therefore we had a detailed look at these countries. And also the potentials which are foreseen will most likely be the biggest one in these markets for the European picture. And the question is, what is the impact of increasing heat pump implementations? When I'm talking about implementation, this is more or less equivalent to sales. So what's the impact if heat pump sales go up on these 8 different markets within the European Union? That's the question. And within the scope are the energy demands for heating, hot water, cooling, and auxiliary energy. So all these standard purposes that are relevant when we're talking about heat pumps. We did the analysis within 3 different scenarios that I want to define a little bit more in detail on the next slide. 3 different scenarios, yes. For all 3 scenarios, we had the same development in terms of energy-saving measures to the buildings. So the building shells, the qualities of the building shells, for example, for walls, for ceilings, for windows, for other components are exactly the same in all the different scenarios, but the main difference is about the heating system mix we apply, or the cooling system mix. So the HVAC systems that we are putting in place for these 3 scenarios. And the first one is the current policy implementation scenario with moderate increasing heat pump shares starting from the status quo. So we're looking at the different markets and first analyze, okay, what's the share of heat pumps and other technologies in the markets, and that's the starting point. And then we take into account the policy that's already in place there, so the implementation of the current policy, and make our expert judgment on what will happen in that market up to 2020, 2030, taking into account just this policy implementation that's already in place. So that's starting from the status quo going up to a current policy scenario, and the other ones are a little bit theoretic because the next scenario is the HP+. Here we say for all retrofits that are carried out in that scenario, 30% will be equipped with heat pumps. And for new buildings, it will be 50%. which is a bit higher because in new build situations it's more easy to implement heat pumps compared with retrofit situations because the circumstances are so it's easier to implement heat pumps in the new build concept rather than in a retrofit concept. So that's the second track, the HP Plus, and the HP Double Plus scenario is even more ambitious in terms of systems applied. Here we assume a 50% share of all retrofits are done with heat pumps and 100% share of all new builds with heat pumps. So there's no other technology left for new buildings, and half of the retrofits are done with heat pumps basically. There is some comments, some footnotes to that definition, and I will tell you about later on. But in general, that's the basic scenario definitions that we did. Let me tell you a few words about the key messages we came up with. First one is about the greenhouse gas emissions. When we're talking about greenhouse gas emissions, here in that study, it's on the one hand side CO2 emissions from heat pumps, but at the same time greenhouse gas emission equivalents from leakages of F-gases. And that's the two things you see in that graph. And let me take the arrow to show you. Here you see the development starting at 2012, greenhouse gas emissions from heat pumps in buildings. Or not from heat pumps, but that's the greenhouse gas emissions from all systems in buildings. Total greenhouse gas emissions from the building sector, and that's 8 countries. And then you see the development from 2012 going to 2020 up to 2030 in these 3 different scenarios. Here you have the current policy implementation scenario, the red one, and then the dashed line in blue is the HP Plus, and the dashed line in green, HP Double Plus. And this is different developments from 2012 up to the target year 2030. That's the one point. It's not the same development, only because of the different definition of heating systems in place. So in the red current policy implementation path, there's very little heat pumps compared with a situation with very much heat pumps in the HP Plus Plus or Double Plus scenario. Because, yeah, the definition on the slide before, it's more heat pumps in retrofits and more heat pumps in buildings. That's one thing. The gray field that you see here, starting in 2020, going to here in 2030 and up to 2050, that's the building sector specific target corridor that comes out from the European roadmap moving to a competitive low carbon economy in 2050. So that's more or less the target corridor that the building sector needs to go from today via 2020, 2030 up to 2050. So that's the way to go. And here you see what happens in the building sector of these 8 countries. And you see that emissions are decreasing over time, and from a certain point onwards, you see that these tracks have different tracks. And in the current policy implementation in 2030, you are within that corridor. For the HP Plus, the same, and HP Double Plus is even better than the target corridor in 2030. That's one thing. But the other thing is that targets are getting more ambitious in the period from 2030 up to 2050. And you see this here, the slope increases of the target corridor, basically. And therefore, we recommended to go for a very ambitious track in terms of heat pumps if the target should be just met with heat pumps, because targets are getting more ambitious, but the effect of measures like heat pumps and other things in building sector is rather decreasing than increasing over time. So that's a very, very interesting thing to see, that the target is getting more ambitious, but the measures are decreasing in their effectiveness. Right. And then that's the story about the CO2 emissions from the building sector itself. And the second thing that you see in that graph is that the CO2 equivalent emissions from F-gas leakages. F-gas is that's, so to say, the filling of the heat pump. That's the gas the heat pump needs in order to operate. And there is leakages because it's not 1000% sealed, the system themselves. and there's a small leakage rate during production, manufacturing, etc. So this is the second effect we have here for the different tracks. There are different leakages, and you can transfer the leakages in greenhouse gas emission equivalents, and that's what we did here. And you see that for the most ambitious renovation track or heat pump track, the HP double plus, the greenhouse gas emissions from leakages are the highest, and the other ones follow then a little bit below. And that reason is simply because in the green dashed line in the HP double plus, more F-gas is used because you have more heat pumps installed. And that's a very important effect for heat pumps that you need to take into account when you're talking about the positive effects of lowering greenhouse gas emissions from usage of heat pumps. You also have a more or less small rebound effect from the emissions of the leakages. That's very important to take into account and to just account for. Yeah, and in numbers, the total CO2 emissions reduction from 2012 up to 2030 can be 46% in the most ambitious renovation track, which is of course a little bit theoretic because, as mentioned before, 50% of all retrofits are equipped with heat pumps and 100% of new builds. That's kind of a theoretical upper limit. It's not very realistic, but it's the upper limit, and we just wanted to show the upper limit here. Second key message is about final energy, and we can say that the final energy is decreasing from 2012 up to 2030 by 19% in the current policy implementation scenario, 25% in the HP Plus and 31% in the HP Double Plus scenario. And as you see, the numbers are smaller than the savings in greenhouse gas emissions, and that's due to the changing emission factor of the electricity that is used to drive heat pumps. We have an effect on the final energy, but an even bigger effect on the greenhouse gas emissions because the electricity mix is changing over time. So that's the key message on final energy here. Third key message is on total annual costs, and that's very interesting because we not only addressed the technical issues, so energy and emissions in the study, but we also looked at costs. And when you talk about costs, it's always important to keep an eye on the investment costs. What investments do you need in order to equip a building stock with more and more heat pumps on the one hand side, and the running costs in terms of energy costs are the other important driver on the cost side, and therefore we looked at investments and energy costs. And the indicator we analyzed was the total annual costs, and that's basically the annuities from the investments and the energy costs per year. So it merges both indicators, the investment costs and the energy costs together, and that's quite transparent because you can then just compare annual numbers between different scenarios with different investments and different energy costs. So total annual costs is our cost indicator, and here you see that starting at 2012, the total annual costs are increasing in all tracks because in the current policy implementation you have some heat pumps installed, of course measures to the building shell, but they are always the same for all different tracks, and you have costs for heat pumps and other heating technologies, cooling technologies. And for the HP Double Plus, for example, you have more heat pumps than for the CPI scenario. But on the other hand side, you have probably lower energy costs because heat pumps, running heat pumps is lower in terms of your energy bill than firing a gas condensing boiler, for example. But the message is that the costs in the HP Plus scenario are just 0.7% higher in 2030 compared to the current policy implementation scenario, and 2.7% higher in the HP Double Plus. So that's quite a reasonable number. It's not about 10, 20, 30, 50% more or even more, but it's a very small number. And if you change a little bit your assumptions on investment costs or energy costs, that may change. So the message is here that's quite the same, the annual costs. to show that high shares of heat pumps are not necessarily more expensive than other technologies or other paths. And the last key message is on renewable energy shares. On the left-hand side, you see the renewable energy shares from the National Renewable Energy Action Plans. That's by 2-point-something% for that 8 countries. And on the right-hand side, the red, the blue, and the green bar are the shares that you're targeting in 2020 for the different tracks. And you see that these heat pump shares in that situations are much higher than promised in the national needs. So message here is that we don't have any problem with renewable shares if you go to high implementation of heat pumps. Okay, that's a brief overview on objective and key messages. And now I want to go a little bit more into details and show you a little bit more about the model and the methodology and the detailed results. I think that's the first one. Let me see. Okay, let's start with that one. This is a very detailed calculation structure of the model itself. It was developed during my dissertation the last couple of years. But what you basically see is different steps of calculation of these scenarios. And you could start having a look at number 1. This is all the data that you need for the building stock. Number 2 is about climate data in that specific country. Number 3 is the floor area calculation for a specific country. That one here, you see calculation of floor area, and that's always dependent on different drivers. What is your assumption for new building rate? What is your assumption for demolitions, for retrofits? What about the quality, etc.? And these are all drivers to the floor area development in a country. Floor area assigned to different reference buildings, to different qualities of building shells, to different technologies, etc. So that's your building stock inventory, numbers of buildings or floor area. That's exchangeable. And then you have your scenario parameters with that key drivers to the floor area. And together they are input for the calculation of useful energy and energy demands here. And for all different situations or combinations from reference buildings, qualities of building shells, technologies, etc., the energy demands for heating, cooling, hot water, auxiliary energy, etc., are calculated within that box. And from 5 it goes to 6. That's the final energy then. Basically, depending on the useful energy for heating and cooling, you come up with the final energy, taking into account conversion rates, etc., for all the systems, and that's done for cooling at other appliances as well. And from 6, you have the opportunity, or you can just make a calibration if you have some top-down data from statistics, which is that box here. You can do a calibration and come up in the end with the heating and cooling loads. So that's the size of the system you need within a building. If you have a high cooling load, you need a big heating system. If you have a small one, because you have a very good insulation, for example, on the walls and the roof, you have a small heating and cooling load. And in box number 7, the economic assessment is done. Here is all the different economic indicators are calculated here, like the investment costs and the energy costs, etc. And in the end, greenhouse gas emissions and primary energy are calculated from the final energy, and some more assumptions. So that's the basic setup of the model we're using here. And the last graph about the methodology, that's the scope of the model. If you start at the right-hand side, that this could be the scope of one building, and you start on the right-hand side, for example, with the primary energy input to a building. That might be your gas delivery or oil delivery, or the electricity you're just putting into the building. And then you have all kinds of different transformation processes within the building. You have, for example, a gas boiler and that transforms your primary energy into heat, and the heat is then heating up your room, etc. And all kinds of energy flows within here. We could just easily talk about this here half an hour, but I think that's not the target of the webinar today. So I will just address the basic things here, and it's basically a transformation process from primary energy up to the heat and the cold and the services you want to have within a building. And all these different transformation processes, including renewable energies, are covered by the model. Right, if we go on then to the scenario definition, I said that we did the assessment for all the 8 countries within Europe. And here you see the input data concerning the building stock of the 8 countries. On the upper left side, you see a graph of the conditioned floor area per country and building type. For example, that blue one here is for Germany, the single-family buildings. And here you see million square meters. And this here is multifamily buildings, so blue and green is residential buildings always, and all the other colors are non-residential buildings basically. And that's about the floor area development. Starting with Germany and the biggest building stock down to Austria was the smallest one. And in the graph on the lower right side, you see number of buildings, and you see here that Germany has the biggest building stock in total, followed by France, UK, Italy, etc., and so on. And that's always a little bit different. On the left-hand side, you have the square meters. On the right-hand side, the number of buildings, and they don't need to be in the same order. That could be different. It depends always on the average size of the building types. Right, what we have here is the different reference buildings. In the slide before, we have seen that it's about the analysis is about residential and non-residential buildings, and here you get an impression of what reference buildings are behind these type of calculations, because you cannot do the calculation for every single building. You need to have reference situations with different parameters. And the first step for these reference situations is to have the reference buildings. That's about the geometry of the buildings. And you can see this is, for example, a single-family house. This is a multi-family house. This is a non-residential office building, I guess. This is something like a school. And you see for different countries, we have different reference buildings. That's a small fraction of all the buildings that we have. But it's just about, we are assuming these kind of things there. Apart from the reference buildings, we need to have some assumptions on the different drivers per country. I mentioned before that a certain new building rate, a certain demolition rate, a certain retrofit rate needs to be the input to the scenario calculation. And here we always look into that country and start with the current retrofit rate, for example. And of course, that's different per country, and here's the assessment country by country, and you can see that, for example, in Germany, the renovation rate for residential buildings is higher than for France, for example. Or you see in the lower part that the renovation rate for non-residential buildings in Germany is lower than, for example, in Spain. These kind of things. That's an assessment of the situation in the different buildings to start with. And that's of course modified then in the scenarios. We assume increasing activities in the building sector, especially retrofit rates, because we want to meet certain targets for energy and greenhouse gas reductions, and therefore we have certain assumptions there. But they're all the same in the different scenarios. Right. This is again the definition of the different scenarios. And here we have it again for the current policy implementation scenario. Here we assumed a full and timely implementation of all legislation related to energy performance of buildings, and especially heat pumps by the member states. So as mentioned before, all the policy that is currently been discussed or being implemented will be implemented. That's the assumption, and nothing really more. So that's kind of a baseline thing. And in the second scenario, the HP Plus, ambitious heat pump scenarios with increasing shares of heat pumps in new buildings and retrofits. And as I said, here's the target, a 50% share of heat pumps in new buildings and a 30% share in retrofits. And HP Plus Plus, Double Plus, basically the same, just with different numbers. It's a 100% share for new buildings and a 50% share in retrofits. And the indicator saying it's 50, 30, or 100% is the implementation shares gained from competing technologies. It's down here in the explanation, and what that means is shown on the next slide. For the first scenario, the current policy implementation scenario, we have the definition of a leverage factor. If we assume that a country is very good in implementing the current policy, or the policy that's currently being discussed, we say, okay, it's more likely that these things are going to happen in the next couple of years, whereas in a country where the policy implementation is not so good, that factor is not as high as for the other country. And therefore we have a leverage factor on the current development of heat pumps, and it depends always on our expert judgment whether it's good or not, and we come up with a leverage factor. If the impact of recurrent policy is not there, it's basically 1, so there's no change to the heat pump shares that we will see in the future. If the impact of the current policy actions or discussions is rather high, we come up with a 2.0, and then the implementation shares are more or less doubled for the future in a very simple, to say it very simple. It's a bit more complicated, but that's what's basically behind. That's the definition for the current policy implementation scenario, and for the two heat pump implementation scenarios, HP Plus and HP Double Plus, it's a bit different. And here we ask ourselves the questions, starting from a situation in 2012 that you see here. In the left bar, you do have a yearly sales of heating systems, for example. So small share of heat pump sales and other systems that are sold year per year in the country. And we ask ourselves the questions, okay, what is the implementation shares for heat pump gained from competing technologies? So what's the share from the blue column, from the blue bar here, that can be equipped with heat pumps in the future? And therefore we came up with the indicator implementation shares gained from competing technologies, and that's basically the red part here. So increasing heat pump shares that are currently being equipped with other systems, but not with heat pumps. And the definition that you have seen on the slide before, for example, the 50% in new buildings and 30% heat pumps in retrofit for the HP Plus scenario, that's always that red part here, excluding the sales or the implementations that are done year per year anyhow with heat pumps. So it's the additional share of heat pumps. Right, and the reasons why we are doing that is the market saturation curve. When you have a more detailed look and analysis for heat pump markets, or in general for market developments, you will see that there is a market saturation. When the technology starts, it is very slowly entering the market, and from a certain point, it really starts to increase. The sales increase, and then the slope is at maximum in the middle. That's somewhere here, and then when it goes to almost a market saturation, the slope is decreasing again of such a sales curve, and it is more or less stable, and the sales are more or less the same year per year. And then we ask ourselves, okay, with respect to heat pumps, what countries have growing heat pump markets? And what countries have more or less saturated markets, and then we came up with that map here for the different countries. Most of the countries are growing heat pump markets, so the shares or the sales, the numbers of heat pumps sold year per year are increasing every year, and only for Sweden it's more or less a saturated market. There's no much more potentials to sell because of different reasons. And that's the argumentation behind why we have these different indicators and the implementation shares from competing technologies. So that's in line with the market saturation curve. And the result of that is that we then can calculate the heat pump implementations per year. And this is a graph on the left side here for all countries. And what you see here is the numbers of heat pumps sold in all 8 countries. Starting with the numbers of heat pumps in 2012, there are different developments for the current policy implementation, for the HP Plus and the HP Double Plus scenario. And of course, in the HP Double Plus, sales are at maximum in 2030. And to illustrate the difference, we came up with a second graph showing the relation of heat pumps per scenario in 2020 related to in 2030, related to 2012. That's the graph on the right-hand side. And you see here 100% sales in 2012. And when you follow the current policy implementation track, you end up with 206% of the sales in 2012 by 2030. And if you go for the HP Double Plus track, you end up with over 700% of the sales from 2012 by 2030. So that's quite a big difference. And that shows why these differences are so substantial. Yeah, and then some results for individual buildings, because we not only did the scenario calculations for all the building stock, but we did some underlying calculations for single individual buildings to calculate some parameters like the seasonal performance factor, for example. And what you see on the left-hand side is a table showing the seasonal performance factor for different countries, Austria, Belgium, France, etc., and for different heat pump technologies on the left-hand side, and for different heating systems within the building. For example, this is a 55-degree design temperature system. That's a low temperature 35-degree system, and that's the domestic hot water production. And the seasonal performance factors are always different, of course. And taking into account these different seasonal performance factors for heat pumps, you of course end up with different final energy demands and different CO2 emissions. And on the lower right-hand side, you see an example for Austria with the CO2 emissions for 3 different reference buildings, a single-family house, a multi-family house, and an office building with different heat pump technologies. For example, brine heat pumps, air heat pumps, water heat pumps, gas heat pumps. And you see the comparison in terms of CO2 emissions, just to drive that heat pumps. And we have these kind of data for all the different countries, different reference building and different systems. That's just an example for that situation in Austria. Yeah, and then again, this is the graph on the greenhouse gas emissions, because that's the most prominent result we were producing. One thing I missed in the beginning is probably, here's a point saying this would be the CO2 emissions without any heat pumps. And that's the calculation we did on short notice, because the Heat Pump Association was asking, yeah, that's very interesting, the results, but we would like to know what would happen if we don't have any heat pumps at all in the building stock. And that's the number we came up with in 2030. And you see that having no heat pumps in the stock would lead to greenhouse gas emissions in 2030 that are not in line with the long-term targets, with the gray area here. And that's an overview of the results, of all the results, or of the most prominent results that you also find in the executive summary of the study. It's again an overview of the 3 different renovation or scenarios, and it says something about the energy reduction in the first column, the CO2 emission reduction potential, which is minus 34% in the current policy by 2030, minus 46 in the HP Double Plus scenario. It gives you some information about the final energy in 2030, primary energy as well. And here you have the comparison of the total yearly costs. That's very important as well, and we addressed it before. And here you see the amount of, in the next column, the amount of F gases needed for the production of the heat pump. and that's directly related to the number of heat pumps. And then the last column, that's the greenhouse gas emissions from F-gas leakages in that heat pumps in 2030. But we addressed it also before. Right. I have 3 minutes left and will come up with some conclusions. The high implementation of heat pumps, as we have seen, can significantly contribute to the mitigation of CO2 emissions on the long term. And that's one very important puzzle piece of the future energy and system mix within buildings, because the electricity that drives the heat pumps is getting greener and greener over the years, and therefore if you invest in a heat pump today, it automatically gets more greener over time, so to say. And very important, heat pumps or more heat pumps can be realized to moderate additional costs. And we have seen that because the additional costs are in a very small percentage, and it's very sensitive to any changes in investment costs or energy costs, and that might change. And therefore the overall picture is that heat pumps are substantial, are important for the future mix within buildings. And if we go to high implementation scenarios like the HP Plus or even targeting HP double plus scenarios, it's very important to have additional policies in place, because as we have seen, the current policies are not enough to support these high heat pump implementation shares in the future. Yeah, thank you very much for your attention.
Okay.
And I'm happy to take questions.
Okay, thank you.